Hi everyone, this is Sai Teja from CSC AML section B. Today my topic is about hydrogen energy. Let's start the session. Salinated features of hydrogen energy. Hydrogen has highest energy content per unit of mass of any chemical fuel and can be substituted hydrocarbon in a broad range of applications. Its burning process is non-polluting, heating value of 28,000 kilocalories in 3 times greater than hydrocarbon. Easy in production because it is produced from water found in abundance. Hydrogen is highly flammable. Hydrogen at ordinary pressure and temperature is a light gas with a density only 1 by 14 that of air and 1 by 9 that of natural gas under the same condition. By cooling to extremely low temperature of minus 253 degrees Celsius, the gas is condensed to a liquid with a specific gravity of 0.07, roughly 1 by 10 that of gasoline. The flame speed of hydrogen burning in air is much greater than for natural gas, and the energy required to initiate combustion is less. Mixture of hydrogen and air are combustible over an expectationally wide range of compositions. Thus, the flammability limits at ordinary temperature extends from 0.4 to 74% by volume of hydrogen in air. Production of hydrogen. On the basis of source, use an energy source hydrogen production of following type. Electrolysis or electrolytic production in electrolysis water split into H2 or O2. When electric current passes through in this process, two types, two types of electrolyzers used. Tank type electrolyzer, bipolar or filter press electrolyzer. Thermochemical methods. Some, some thermochemical cyclic process. Westinghouse electrochemical thermal sulfur cycles, Mark 13 cycles, iodine sulfur cycle, fossil fuel methods, solar energy methods, biophotolysis method, photoelectrolysis method. In the diagram, we can observe electrolysis or the electrolytic production of hydrogen. In we can see at the red color cathode and the blue color anode. Red color indicates the hydrogen and blue color indicates the oxygen. You can observe through the diagram. The process of splitting water into hydrogen and oxygen by means of a direct electric current is known as electrolysis. This is the simplest method of hydrogen production. Although only the water is splitted and electrolytic is required because water itself is a very poor conductor of electricity. Theoretically, 1.23 volts are required for this process, but in real situation, due to the slowness of the electrode process, higher voltages are required for the electrolysis. Theoretically, 2.8 kilowatts of electric energy should produce from 1 gram of hydrogen. However, the actual electrical energy requirement is generally from 3.9 to 4.6. This means that efficiency of electrolysis is roughly 60 to 70%. To increase the efficiency, the electrode surface must be able to catalyze the electrode processes. Platinum and nickel are normally deposited on the electrode. Diaphragms prevent electric contact between adjacent electrodes and passage of dissolved gas or gas bubble from one electrode compartment to another without applicable resistance to the passage of current within the electrolysis. Asbestos is the most suitable material for cell diaphragms. Three major factors determine the usefulness of an electrochemical cell from hydrogen production. First one, energy efficiency. Second one, capital cost of the plant. Third one, lifetime of the cell and its maintenance requirements. A number of advantages can be gained from operating electrolyzer at higher pressures as follows. Reduction in specific power consumption, delivery of gas at pressure, thus eliminating the cost of gas compressor. Reduction in the size of electrolysis cell. Two types of electrode arguments are used by industry for the electrolysis of water. On this basis, they are classified as follows. Tank type electrolyzer and filter press or bipolar electrolyzer. First one, tank type electrolyzer. The first application in the industry used the tank electrolyzer, in which a series of electrodes alternating anodes and cathodes are suspended vertically and parallel to one another in tank filled with 20 to 30% solution of KOH in demineralized water. We can observe the diagram which was shown on the screen. We can see left side parallel nodes and right side parallel cathodes, and there is a power supply, and we can see the electrochemical reactor, and we can observe the diagram. Alternate electrodes are surrounded by porous diaphragms, impermeably to gas but permeably to the cell's electrode, like that prevent the passage of gas free from one electrode compartment to another. All the anodes are connected to the same positive terminal of the direct current source, and all the cathodes are connected to the same negative terminal. The major advantage of tank type electrolyzers are twofold: relatively few required and those needed are relatively inexpensive. Another advantage of this argument is that individual cells may be isolated for repair or replacement simply by circuiting the two adjacent cells with a temporary busbar connections. Disadvantage is the inability to handle high current densities because of cheaper component parts, inability to operate at high temperatures because of heat losses from large surface areas of connected cells. Filter press electrolyzer. Uh, This is the most widely used electrolyzer system because of its specific resemblance to a filter press. Except at the ends of the cell, the electrodes are bipolar, that is, one phase of each plate electrode is in anode and the other phase is in the cathode. Because of cells can be made relatively thin and large. Except all the ends of the cell, the electrodes are bipolar, that is, one phase of each plate electrode is in anode and the other phase is in cathode. Because of the cells can be made relatively thin, a large gas output is achieved from a relatively small volumes. Thermochemical methods. The overall efficiency for the conversion of primary energy from nozzle and nuclear fuels in hydrogen by electrolysis is dependent. In the first place, on the efficiency of the generating electricity. This efficiency is 38% for modern fossil plants and 32% for nuclear installation. The higher conversion efficiency might be possible if the heat produced by the primary could be used directly to decompose water within the intermediary of electric energy. Such direct decomposition into hydrogen and oxygen is possible, but it requires the temperature at least 2500 degrees centigrade. But due to temperature limitations and conversion process equipment, direct single-step water decomposition is not possible. However, a sequential chemical reaction series can be devised in which hydrogen and oxygen are produced. Water is consumed and all other intermediates are recycled. The operation is called as thermochemical cell. It is so called because energy is supplied as heat at one or more of the chemical stage, and hydrogen and oxygen are produced separately in different stages. For practical reasons, primarily the availability structure and containment materials, the maximum temperature considered to be about 950 degrees centigrade. Heat energy then be converted into hydrogen energy with efficiency of 50%. This is a marked improvement over what is possible by electrolysis. At present, no commercial process for the thermal splitting of water to hydrogen and oxygen is in operation. Several workers have proposed many multi-step reaction sequences that thermally decompose water at lower temperatures. We can see few examples, and as can be seen in these reaction sequences, only water is split. All other materials are completely recycled. Some thermochemical cyclic process. Numerous candidate cycles have been suggested during past few years. Uh, we shall consider only three cyclic processes which are as follows. Westinghouse electrochemical thermo sulfur cycle, ISPRA Mark 13 bromine sulfur cycle, iodine sulfur cycle. Westinghouse electrochemical thermo sulfur cycle. Here is a few reactions we can observe. It is cleared by summing reaction that overall process decomposes water into hydrogen and oxygen and involves only sulfur dioxide as recycling intermediates. Although electric power is required in the electrolyzer much smaller quantities than those necessary for the cooling. Ispra 13 cycle. We can see some reactions about it, electrolysis and the thermolysis. The somewhat lower cell voltage in the Westinghouse process is counterbalanced by the advantage of the higher concentration of sulfuric acid obtained in the Mark 13 process. It should be also mentioned that in incorporation of an additional element bromine in the Mark 13 process may also be advantageous since it offers more possibilities in the industrial operation of the process. Iodine sulfur cycle. Among the purely thermochemical cyclic process, those belonging to the iodine sulfur family are of most interest at three present stages. We can see some equations. The main difficulty in this process lies in fact that if inside reactions are to be avoided, the two acids can be obtained only in dilute solutions. The difficulties associated with this process have led in recent years to numerous investigations and suggestions for modifying the process. Fossil fuel method. Mostly a gaseous mixture of CO and hydrogen is formed in the first stage. This popular method of hydrogen production, though which about 94% hydrogen by using following different process. Stream reforming of gas, partial oxidation of heavier hydrogen carbon, coal gasification, pyrolysis, biomass gasification. Here is the equation to remove the CO. The mixture is submitted to the water gas shift reaction with steam. The CO is therefore converted into CO2 with the formation of additional hydrogen and energy. Hydrogen production by the iron process. We can see the diagram hydrogen production by the iron process. Fe plus H2O gives rise to FeO plus H2 and the formation of the iron through the hydrogen production. Steam gasification process and its application. Steam gasification process and its application. We can see the diagram of table about cold stream and further divided into steam gasification and allothermic heat. We can observe the different stages which will converting. We can see the gas generators for present day industrial coal gasification. We can observe the diagrams. Solar energy method. Hydrogen production from solar energy. There is two methods are considered. First one biophotolysis and the second one photoelectrolysis. Biophotolysis. This method utilizes living systems to split water into its constituents hydrogen and oxygen. In normal photosynthesis, in the green pigment chlorophyll takes up the energy from sunlight and in a complex series of reactions breaks up water molecules into oxygen gas, hydrogen ions and electrons. The oxygen is involved from the green plant, but the hydrogen ions are and electrons are removed by the interaction with carbon dioxide to produce simple sugars. Certain single cell green or blue green algae are able to make enzyme hydrogenous. They decompose water in sunlight to yield hydrogen and oxygen. Instead of using living algae to obtain hydrogen from water, a more convenient approach is to utilize biological materials obtained from plants or bacteria. One advantage is the ability to vary the conditions to optimize hydrogen production. An ultimate object of research on the decomposition of water by sunlight, the efficient simulation of biological process without using biological materials. Photoelectrolysis. In photosynthesis, a current is generated by exposing on or both electrodes to the sunlight. Hydrogen and oxygen gases are liberated at the respective electrodes by the decomposition of water, just as ordinary electrolysis. At least one of the electrodes in the photosynthesis is usually a semiconductor. A catalyst may be included to facilitate the electrode processes. Research is being directed at increasing this efficiency by selection of electrode materials, electrolyte solution, and electrode catalyst. Electrolysis is a more attractive way of producing hydrogen with solar radiation since it can be operated intermittently and therefore needs no storage. The solar electricity need from electrolysis can be produced either photoelectrically or thermoelectrically. Both technologies are available today. You can observe the hybrid electrolysis diagram. The solar electricity needed for electrolysis can be produced either photoelectrically or thermoelectrically. Both technologies are available today. Stream methane reforming process. We can observe how the stream methane reforming process will occur through the diagram. Hydrogen as an alternative fuel for motor vehicle. We can see few tables about it. Advantage of hydrogen energy. Not explosive in open air, not decomposing, not self-ignitioning, not oxidizing, not toxic, not corrosive, not polluting, not cancer causing. These are the few advantages of hydrogen energy. We can see the disadvantages. Currently more expensive, hydrogen is more difficult to store and distribute. Status of hydrogen based tech in India. The BHU Murugappa Chettiar Research Center, Chennai at IIT Kharagpur are leading institute. BHU developed metal hydride with storage capacities 2.4 weight percentage. MNRE shared projects in 22 universities. In IISc Bangalore, research work on process to hydrogen-based fuel cell. Some other projects in progress in private sector. BHEL installed 200 kilowatt fuel cell based on power plant. We can see we have lot of advantages about the hydrogen one, but the same way we can have the few of the disadvantages about the hydrogen because it is more expensive of cost and it is a more difficult to store or distribute. Thank you all.